Hi everyone, my name is Jack Cook. I'm a master's student at MIT, and I'm going to be presenting alongside Jules Dreen, a graduate student also at MIT. We're here to present There's Always a Bigger Fish, a clarifying analysis of a machine learning assisted side channel attack. This work was also done with our other author Jonathan Behrens and our advisor Mengjia Yan. I'll pass it to Jules to start us off.
Cool, yeah, thank you, Jack. So nowadays people use machine learning to mount very powerful side channel attacks. These attacks are great, they're highly effective, and they even work in the presence of noise. But this talk is a cautionary tale. Indeed, these machine learning assisted attacks use machine learning as a black box, and they can find any correlation between an observed signal and a victim secret. The problem with that is that these attacks are very hard to interpret. And the problem with the fact that they're hard to interpret is that if we don't really understand these attacks, developing effective defense mechanism can be very challenging. And so we think that this can only be addressed by doing better attack analysis. And today we'll present Bigger Fish, which is a detailed analysis of a misunderstood side channel attack. So this is the agenda. I will first go over some background, then I will walk through a surprising experiment, and then Jack will take over to do an in-depth security analysis of the attack we're looking at today, and finally we'll conclude with some finding and a conclusion. So let me start with some background. Timing side channels. So the idea here is that if you have several orthogonal independent programs running on the same machine, they will end up sharing a lot of common resources. Think about branch predictor, shared cache, or the DRAM controller. And so if there is contention over these resources, the activity of the blue program up there might have an influence on the timing of the red program. And now if the red program is malicious and controlled by an attacker, the attacker might observe the timing of its own operation very closely and try to infer a secret from the behavior of the blue program. In particular, it might collect some signal traces from its own execution, like the time it takes to perform a memory access, for instance, and then try to decode it. So here, decoding the signal means to find a correlation between the signal and the actual victim secret. And this is where machine learning can be especially handy, because it's naturally very good at it. One example of an attack where the signal can be very complicated to analyze is website fingerprinting. And people are extensively using machine learning for this. So in this type of attack, website fingerprinting, the victim program here in blue is a web browser, and the attacker tries to guess which website the victim is currently visiting. So let me tell you more about why fingerprinting attacks are so powerful. So as I just said, the goal of website fingerprinting attacks is to leak sensitive information about a victim by spying on their web browsing activity. So these attacks are pretty bad because they're very dangerous because they can leak a lot of private information about the user. Think about all the websites you visited in the last 24 hours. It might tell a lot of information about you, like your religion or your political inclination. These attacks are pretty bad because they're also pretty easy to mount. Like an attacker program can be run directly in JavaScript by in a malicious page, open in another tab of your web browser, and that's very powerful because it only requires an attacker with very low privileges. And finally, this type of attack is perfect to exploit a side channel, and it's a very good fit for a machine learning-based decoder. Let me actually walk you through how machine learning classifier can be trained and used in this setup. So first, we have an offline phase or training phase, where the attacker is going to create a training set by collecting an important number of traces from a set of popular websites. So these traces are labeled with a corresponding website and used to train a machine learning classifier. Once the classifier has been trained, the online phase of the attack can be carried away. The attacker will collect a trace corresponding to the actual victim activity and ask the machine learning classifier to infer which one of the popular websites was visited by the victim. So this method is very robust and can make it possible to exploit very noisy and cryptic side channel signal that would be extremely difficult to analyze otherwise. So far I've told you how the machine learning classifier can use these traces. So now let me tell you how we collect these traces using side channels. So this is the specific existing attack we're going to analyze today. And it's a cache occupancy attack. So we've put the attacker codes on the left-hand side of the slide. And as you can see, the code is pretty simple. Let me describe it to you, I guess. So you have this outer loop that will basically constantly run. And inside of this loop, we'll first initialize a timer and then a counter. And then you have this second inner loop, this while loop that will basically measure 5 milliseconds. And inside of this inner loop, the attacker will increment a counter and perform some cache sweeps. And so at a high level, what this code is doing is counting the number of time an attacker is able to sweep the entire cache every 5 milliseconds. So that's also why we call this attack sweep counting attack. So as a result, given this code, it's kind of easy to assume that the side channel exploited in this attack is the cache. And the intuition here is that one after the other, the victim will put some elements in the cache, and that will impact the timing of the cache sweep the attacker performs again and again. But now let's look at the surprising experiment. In this experiment, we'll keep the same attacker code, but we'll remove the cache accesses from the code. And so if we now look at what's left, it seems like we're only incrementing a counter and saving its value every 5 milliseconds. So at a high level, what this code is doing is profiling the instruction throughput of the attacker. So now if I ask you, what should the attack accuracy do? If we actually remove the memory accesses and we think that we're observing a cache side channel, well, the accuracy should drop, right? But that's where it becomes interesting. Here's a sample from our results. So this is the accuracy for an attacker to guess which website was visited by the victim out of a set list of 100 websites. You can see that our results are consistent over diverse configurations, and our attack performs better than the sweep counting cache occupancy one. For instance, for Chrome running on Windows here, the sweep counting attack has 80% accuracy, while our attack performs better with 93% accuracy. So given the surprising results, now we might ask ourselves the following questions. Which primary side channel are these two attacks actually exploiting? And so it's important to understand that this is kind of a challenging problem. The reason is that there's so many hardware resources shared between these two programs that really finding the primary source of leakage is kind of difficult. And we don't have specific techniques or method to answer this question. Okay, so far, I hope I've convinced you that machine learning assisted attacks are kind of hard to interpret. And in the rest of the presentation, Jack will show you how we've performed a detailed analysis of that attack and what is the root cause side channel that we've actually discovered.
Thanks, Jules. So at this point, we essentially have a machine learning assisted attack that's being powered by some unknown side channel. Now, we're going to analyze it to figure out what this unknown side channel really is. As Jules mentioned, this might be a difficult task because there may even be more than one source of leakage. For this analysis, we're going to return to the classics, the scientific method. We're going to modify our independent variables, run experiments, observe results, and report conclusions. Let's start with our first observation. We have 95.2% accuracy on this website fingerprinting task when memory accesses are removed from the attack. So we went back and did our research, and we realized, as Jules said, that this attack is essentially measuring instruction throughput over time. So what could cause throughput to change? Our first hypothesis was actually frequency scaling. We have this CPU trade-off that's kind of a trade-off between increased performance and energy savings. And our idea was that when frequency scales up, the attacker is able to increment its counter higher, and when frequency scales down, it doesn't increment as much, and that's what causes the side channel. So we run an experiment with frequency scaling disabled on our computer. We train a model, and we get 94.2% accuracy. So our accuracy only went down by 1 percentage point. So our conclusion here is that little to no signal is coming from frequency scaling. So let's do this again. We have 94% accuracy. What else could cause it to change? Our next hypothesis was CPU core contention. Maybe when the attacker and the victim, they're both web browsers, they're pretty complicated processes. Maybe they're doing stuff on the same CPU core, they're contending over the same resources, and that's what is causing the side channel. So we repeat this experiment with the attacker and the victim pinned to separate cores. This time we got 94.0% accuracy, a decrease of 0.2%. So clearly, there's little to no signal from CPU core contention. One more time, 94% accuracy. What else could cause it to change? Interference from system interrupts. This might not be intuitive at first, so let's talk about why we reached this hypothesis. System interrupts are used on every computer to deal with asynchronous events, oftentimes from hardware devices. For example, your computer uses graphics interrupts to render content on the display. Basically, what we thought was happening was when the victim process was loading this website, it was triggering a bunch of interrupts, to download network content, to display stuff on the page, to schedule, the browsers like scheduling all that stuff. And then these interrupts are ultimately processed on the attacker's core. And so in the white region here, the attacker is in user space and it's executing its own code. It's implementing its counter over and over and over again. And then when we reach the orange region, the interrupt handler is run, basically, and we're in kernel space now. And because the core is processing that interrupt, the attacker can no longer implement its counter. It essentially loses all of that time. And so we thought that this was what's causing the side channel. Crucially, and I'll get into this in a second, only some of these can be pinned to specific cores. Some of them can't. So we're going to run this experiment, and we're essentially going to run this experiment with all of the movable interrupts diverted from the attacker's core. When we ran this experiment, we got 88% accuracy, which is a decrease of 6%. So there might be some signal here, but there's still a lot left. 9 times out of 10, the attacker is essentially able to guess exactly which website you're visiting. So there's still a lot of signal. So let's talk more about this distinction between movable and non-movable interrupts. Here we have the proc interrupts file, which you can open up on basically any Linux computer. At the top here, we have all of your movable interrupts. Each row is a different interrupt, and each of the columns that are numbered, we have CPU 1 through 4, 0 through 3. That's the number of times that type of interrupt was executed on that core since the computer started up. A lot of these are very recognizable. For example, on this row, we have interrupts from your mouse. Every time you move your mouse, an interrupt is sent to process that event. We have interrupts from your keyboard, your network card to process, to download, upload data, whatever. SATA interrupts for your hard drive, graphics card interrupts to display content on the screen, and all that stuff. We also have a bunch of non-movable interrupts, and you'll notice that for each of these, the numbers are pretty high on all 4 cores. And this is because this is just how your operating system is designed. These interrupts cannot be pinned to separate cores. Some of these are a bit harder to recognize, but we can still see what they're doing. For example, timer interrupts are used to schedule processes between your different cores on your computer. And IRQ work interrupts are used when there's like a very long-running task, and your kernel can do a little bit of work right now, but it uses an IRQ work interrupt to schedule most of that work for later. So yeah, basically to summarize, these non-movable interrupts are, they're present on every computer. They can't be isolated from any cores. So your attacker is necessarily going to, it's going to hit some of these, and I'll explain that more in a second. They're necessary for the operating system to function, they can't be moved or disabled, and they have not been studied in detail for side channels. So let's go back to this scientific method diagram. We have now 88.2% accuracy with all of the isolation mechanisms that we've applied so far. Frequency scaling, pinning to different cores, diverting all the interrupts. So what else can cause it? Non-movable interrupts. So we want to repeat this experiment with the non-movable interrupts diverted from the attacker. But the problem is that this experiment is impossible. As I just explained, it doesn't matter which core your attacker is on. Some of the non-movable interrupts are going to execute on the attacker's core. So to take this analysis a bit further, we're going to use eBPF, which is a tool that allows instrumentation of the Linux kernel at runtime. We use eBPF to develop a tool that can monitor characteristics of interrupts. We essentially, it probes, we inserted probes that basically record the time at the start and end of each interrupt handler, and we can then correspond this with the timestamps measured by the attacker to see whether those attacker gaps correspond with interrupt handler times. So here are some examples. This is there's a lot on this slide, but let's go through it. So the blue line is the counter values that are recorded by the attacker that Jules was explaining earlier. So at each, as time increases from left to right, these are the counter values that the attacker is recording. The black line is the time that your processor spent handling interrupts at that moment in time. And you'll see that when interrupt handling time increases, the counter value decreases. And this is because, as I mentioned, the attacker essentially just has less time to process this stuff. And we can even notice a couple of spikes here. So for example, when Amazon.com, when we're loading Amazon.com, we have these like drops in counter value at 5 and 10 seconds after you started loading the page. And they correspond with huge spikes in the time that's spent processing interrupts. You can see it there again. When we're loading weather.com, there's like this huge like valley in the counter value distribution, and it's like a mountain in the interrupt handling time. We can even flip them, and you'll see that they actually correspond very well. The blue and black lines mirror each other pretty well. We can even do it one more time just for added effect. We additionally verified with this eBPF tool that 99% of these gaps that the attacker process is monitoring can be explained by the presence of interrupts. We essentially verified using eBPF, using those probes that record the time at the beginning and end of interrupt handlers, that these gaps are explained by interrupts, which really confirms our hypothesis. So there's plenty more in the paper. We have a really interesting randomized timer countermeasure due to the limitations of the browser environment that defeats our attack for the most part. We ran some experiments with virtual machine isolation where the victim and the attacker are in separate virtual machines and saw what that did. We have further discussion of these non-movable interrupts and their security properties, and so much more. We also have an interactive demo that you can try out. Let's see it happening here. So here we're going to collect a 5-second trace on Amazon.com where the attacker process in the background is collecting traces, and on the, you can see we're loading Amazon on the page. I sped it up. We're going to record 3 more traces on weather.com. It's sped up, so you can just see it load 3 times. And then here, we have the traces. You can even see visually that these traces are very different from each other. And when you train a model on this, of course, this is why we get such great accuracy, because machine learning is just really good at figuring out what the label is in these traces given a lot of training data. So to wrap up, our findings and conclusion, machine learning assisted attacks are very powerful, but they can be tough to interpret. This sweep counting cache occupancy attack primarily exploited system interrupts, but because of the black box nature of their machine learning model, it seemed like they were exploiting the cache side channel. Non-movable interrupts have very strong security implications that need to be further studied, and we've released our analysis toolset on GitHub. So I encourage all of you to try out that demo from the video. There's a QR code, and you can just go to that link as well. And this really shows that, in the attack that we've analyzed, researchers thought that the primary side channel being exploited was the cache. Our work shows that interrupt side channels are, in fact, the bigger fish. Thank you, everyone.
For the great talkers, any questions from the audience? Get us started. So what are we going to do with interns?
Sorry?
What are we going to do with interns?
I don't know.
I don't know either.
Yeah, I'm not sure.
I think you need to take that into as well, kind of within your architecture, how these things are moving. I think more for sure how these things are spread around different calls basically. I don't think that's yet.
Oh, hi, nice talk. So I have a question. When you talk about the scientific method, right? You control for one factor at a time, and when you fix that factor and there's little change in accuracy, you say that this factor doesn't contribute much. How can you be sure that the factors are additive? And what if there are other influences such as if you put this factor, this group of factors?
Yeah, so that's a good question. We really tried our best in each of these experiments to only modify one thing at a time. And then in our paper, we explained our methodology where we were generally running like 10 experiments or something, and we took the average of these. We did some t-tests to determine significance of these, single factor at a time. And so we're pretty confident that it's due to those individual things. But there's more info in our paper on that.
Thank you.
Okay, thanks for the brief talk. I was wondering that the cache occupancy attacks are kind of slow. So have you also looked at some faster attacks? And because this is basically you're trying to figure out why these error bars in these attacks occur. And you look at some faster attacks and you have some insights on what might be the cause of the error bars in those attacks.
So just to clarify, when you say slow, do you mean because you need to load it for 15 seconds?
For example, if you like sweep the entire cache, it might be at a speed of milliseconds. Whereas if you do like let's say AES, 810 round AES, fingerprint AES private key extraction might take 1,000 cycles. So it's much faster, but there are some system level parameters that kind of change the accuracy and that goes into that.
Yeah, so I think there are certain things that for this paper, we really focused on the limitations of JavaScript and the browser, where the precision of the timer does not go beyond 0.1 milliseconds in Chrome. So that makes that kind of design impossible. So this paper, the types of attacks that this work is really good for are things like website fingerprinting, where there's like a very clear trace over a longer duration of time, maybe at least 1 second. But there's more that you can do with non-JavaScript environments as well.
Yeah, and I think what we said at the beginning of the presentation is that we hope this is a cautionary tale to kind of understand the high level ideas that is like machine learning is great to run this sectional attack, but you might be a bit careful about it. I'm sure it applies to other attacks beyond website fingerprinting, as you're saying, like AES key extraction or anything sort of different level basically.
Absolutely. Really appreciate it. Thank you. I have an issue for the sorry.
High niche.
Okay,